This is our Physics Notes, Unit 2, Section 2, Forces on Charged Particles. And this is Part 1, where we look at electric fields. So the first thing to consider is if you've got a charged particle, say we have a positive charge there, if you were to bring a small test charge, and by convention our test charges are always positive, then we know that that test charge would be repelled because two positives repel. So let's draw in where the positive charge would go when repelled. It would go there. So as you can see, the small positive test charge is being pushed away. Similarly, if we put the test charge down below, it would go in that direction. And if we had it at the sides, it would go in those directions. And basically anywhere around the main charge that we put this little positive test charge, it would be repelled and move off in a straight line, feeling a repulsive force. So to complete the directions, I'll draw one in here. And what we've constructed is an electric field, and it's called a radial electric field. And this is around what we call a point charge. So it's not the charge on a parallel plate, it's a point charge. And if you look carefully at the field lines, as they're called, you'll see they're all pointing outwards like the radii of a circle. And that's why it's called a radial field. Where the field lines are close, we say the strength of the field is quite strong, and where the field lines are far apart, we say the field is weaker. And that fits in with the general idea of being further away from the charge. You would expect the field to be weaker further away. So the spacing of the field lines is an indication of the strength of the field. This is clearly a non-uniform field. Because it's not constant in strength. Let's just then define what an electric field is. So, an electric field is a region in space within which a small positive test charge would feel what we call electrostatic force. And that force in the diagram I've drawn is a force of repulsion. But of course, if we were to draw a negative charge, negative point charge. Then the field lines would they'd have a very similar shape. They would be radial field lines. But there would be a crucial difference. And that is that the direction of the field lines would be opposite, because a small positive test charge would of course be attracted to a negative main charge, the point charge. So the direction of these lines, these field lines, is inwards rather than outwards, because a small positive test charge there would be attracted. So those are the field patterns, electric field patterns around 2-point charges. Okay, now one field pattern you need to know is the field pattern around what's called a dipole. And a dipole is basically a positive charge placed near a negative charge. And what happens here is you've just got to imagine, where would the small positive test charge go? Well, if it was placed bang in the middle of the two, it's going to be repelled by the positive and attracted by the negative, and so it would do that. And what you find is, as you get a little bit further out, say here, you get a curving line coming round like that. Essentially, when you're a little bit nearer the positive charge, it dominates, and when you're nearer the negative charge, it dominates. And you end up with lines going like this, and the spacing increases between these lines, these big loops, as they come out. And every line leaving a positive charge would end up landing on the negative charge. And these outer lines here, their loop is so big that I'm not showing it, but it is there. And you'd get things like that happening. And you can see that close into the charges, the lines are very tightly spaced. So the field is strongest right next to the charges themselves, and the further away you get, the weaker the field is. Okay, that's clearly a non-uniform field. The field around a dipole, positive and negative charge. The other field pattern you need to be familiar with is that between parallel plates, parallel charged plates. So what we've got here would be a high voltage supply and we would connect it this way to two parallel plates. So let's make this one negative and that one positive. And typically this could be hundreds, if not thousands of volts. So this plate becomes negative, of course, and that becomes positive. So how would the field lines go here? Well, again, if you imagine where a little positive test charge would go, it's going to be repelled by the positive plate and attracted by the negative. So if you popped one right in the middle there, it would just do this. If you popped them right at the end, the end of the plates, you would do that. And similarly at the other end, it's just going to come straight across. And you find with parallel plates that the field is uniform. So when you're drawing these, you need to make the lines look approximately equally spaced. So here we have a uniform field. That's between the plates. If we come outside the plate, we actually have a curved field there with an end effect. Should make it clear that this uniform field is between the plates. Okay. And that's a uniform electric field between two parallel plates. Right. Let's focus in on these plates and look at the definition of the volt. Okay, so let's get our parallel plate. When I'm drawing these parallel plates, I'll very often miss out the power supply, but it obviously has to be there. Otherwise there wouldn't be any voltage to talk about. I'll draw the connecting wires in, and I'll indicate that roughly the same length. I'll indicate that this side is negative and that side is positive. Well, there will be a potential difference between these plates. In theory then, I want this to be a potential difference of 1 volt. Okay, so this is theoretical. We'll imagine the whole thing's happening in a vacuum. Let's imagine that I've got a small positive test charge, and we'll imagine it's Q of 1 coulomb. And imagine that that's where the charge starts. Obviously it's attracted to the negative plate, so it sticks to it. Let's imagine I want to move that charge across between the plates to the positive plate. Well, to do that, I'm going to have to apply a force. And if I do that, then I can move my little positive charge against its will, so to speak, and force him to come to the positive plate. Now, as you know, when you apply a force to an object and move it through a certain distance, you have to do a certain amount of work to make that happen. So I have done a little bit of work in order to force this charge against the field. So moving against the field means it's being repelled by the positive plate that it's heading for and attracted back by the negative plate. If you actually look up at the field diagram, you can see that I'm moving it against the field lines. So our positive charge work is being done. Well, we define the potential difference like this. So the potential difference between the plates is 1 volt if it takes 1 joule of work to move 1 coulomb of charge across. So the potential difference between the plates is defined as 1 volt if it takes 1 joule of work to move 1 coulomb of charge across. So basically what we're saying is that 1 volt is 1 joule of work per coulomb of charge moved. Now we put that into an equation and we say that voltage is the work done divided by the charge. So this is the work done in joules. This is the size of the charge in coulombs, and this is the potential difference, the technical name for voltage, and that's obviously in volts. A volt is a joule per coulomb, and you do often see this written as EW equals QV, or I think in our notes actually W is QV. They're all the same equation. Right, let's just do a little example then. Get my calculator in the hand. So let's imagine we've got our plates. And imagine I've got a charge Q which is positive. I'm going to move it across to the positive plate. So the question is, if the voltage were 5 kilovolts, let's see, how much work, we'll call this party, must be done to move a charge of 1 nanocoulomb across a PD, potential difference of 5 kilovolts. Right. Solution. Well, list our variables. Work done, charge Q, potential difference V. The work done is what we're trying to find out. 1 nanocoulomb, of course, is 1 times 10 to the minus 9 coulombs. And the voltage is 5,000. So the equation is, work done is QV. You find very often, because you're interested in working out the amount of work done, that you very often use the QV version of the equation as much as the Vz over Q1, to be honest. Same equation, of course, just rearranged. So that's 10 to the minus 9 times 5,000. So 5,000 times 1 times 10 is minus 9. And you get the work done is 5 times 10 to the minus 6 joules. 5 microjoules, if you like. So that's how much work it would take to bring our little charge across that potential difference. I'm going to do a part B. The charge is now released. What happens to it? Think about that. Well, we've moved it across to the positive plate against its will, so to speak. So it's already over here. What's going to happen to it if you release it? Well, if you release that charge, it's clearly going to be repelled by the positive plate and attracted by the negative. So it's going to feel a force acting on it by the field itself. And that force, if all of this takes place in a vacuum, is unbalanced. So in fact, it will accelerate. So the answer to the question is the positive charge feels a force created by the field, and as this is unbalanced, it accelerates towards the negative plate. And it speeds up, obviously, as it does so. Okay. Final question in this part then. What kind of energy does the charge have at the 1 positive plate and 2 negative plate on returning? Well, solution here. Well, when it's at the positive plate, you've put work into bringing it across there against the field, against its will, so to speak. That work that you've done doesn't just disappear, it has to be converted into some kind of energy, and it's converted into potential energy. Strictly speaking, electrostatic potential energy. It's a little bit like lifting a ball up in the air. You do work in lifting the ball up against gravity. You're moving against the gravitational field, and when it gets to the top of its height, it's got gravitational potential energy. This is not vertical, of course, but it's a similar idea. You're moving against the field, but you gain electrostatic potential energy. When you let it return, the potential energy changes back, well, because it's moving, it goes to kinetic energy. So the answer is kinetic energy at the negative plate. Now in the next section we'll have a look at some calculations where we can work out the size of the kinetic energy and therefore the speed.